So our next talk this afternoon is going to be Domitilla del Vecchio. She's going to talk about loads in biological circuits, how to engineer modular systems.
Thank you very much, and I would like to thank the organizers very much for inviting me here. So this talk is going to be definitely more engineered here than previous talks. And in particular, I would like to start with a small introduction, right, of the notion of engineering biology. Many people may know, right, in this audience that the notion of engineering biology really started with this idea of creating simple network motifs to understand biological systems. And then at some point there was a transition where people realized we can actually combine all these modules together to create useful systems that can, for example, program cell to chase pathogens, right, in your bloodstream and actually cure illnesses, right? So this is an old movie. It's a neutrophil, it's a white blood cell that is chasing a bacterium, right, in your bloodstream. And the notion is that what if you can re-engineer, right, the sensing, the computation, and the actuation components so that you can engineer these machines, okay? And there are plenty of exciting applications in this field. I won't go through them, but in particular, right, there have been shown that there are some bacteria that can actually localize at the place where cancer cells form. And so the notion is that you can engineer these bacteria to recognize, right, cancer cell, and then they lyse open and produce killing agents, right? So then what I decided to do is to show this one slide. This is based on some of the discussions we have been having yesterday in the panel and also afterwards. So this notion that many people, right, are based on these, I would say, design paradigm, right, from electrical systems where you actually combine systems together to create larger systems, right? And you have this layer design approach. And something that it's really key in the system is that parts and components are being designed such that they maintain their behavior in isolation when they get combined, right? So they are modular by design. And people often tend, right, to think of biology working the same way, but the problem is that biological parts may not necessarily, right, be modular. Nature may not have designed them to compose modularly as you move up in this design algorithm, right? And we know that today, engineering large systems, right, this is a 3-layered circuit that was built in Chris Boyd's lab. It's becoming possible, but it's also taking about 5 to 6 years of a PhD student, right, to create such sophisticated systems with 11 genes, right? Why is that? Well, a big problem is that anytime you have 2 genes in there and you add the 3rd one, then whatever was there does not behave anymore as it was working before, okay? So the notion is that anytime you add a piece, you have to redesign almost completely, right, whatever was in there. So you have this combinatorial and iterative design approach that takes long, okay? So there is a scalability issue. So in this talk, I will take a more systems, control systems view, okay, to these problems. And I will actually start to think what can be sources of context dependence. So why does an input-output system behavior is changing when you add other systems around it, okay? So we have been doing a lot of work also in collaboration with Eduardo for several years with this notion that whenever you have an input-output system and you add connecting, right, another systems, you have that action, right? So you have loads. Molecule that transmit the signal get loaded, right, by whatever downstream system you have. Something else, and we have been doing a lot of work in here, and I won't be talking about this today, because today I want to focus on another big issue, right, that actually started to really look like a bottleneck about 5 years ago, where, right, one realizes that whenever you create circuits, you are creating them within the cell, so you're using cellular resources, enzymes, so you are loading, right, all the cellular resources. And the notion is that 2 systems that may be independent, right, they become coupled through these loading effects, right? And cellular resources, anything, right? RNAP, ribosomes, ATP, right, amino acids, really anything you can think of. And then, of course, there are many other issues, right? Growth is a big one, so your circuits are going to affect growth rate, which is going to impact back the dynamics of the circuit, right? And so what I will be doing in this talk, I will taking a control systems point of view, okay? And view all these red arrows as disturbances, okay? That are acting on your system and trying to think, how can we make the behavior of a system somewhat isolated, okay, from this context? So that said, I will be focusing on a small story, especially related to this notion of sharing cellular resources, okay? And I will start with a very simple example, okay? So this is an activation cascade composed of two nodes. A is activating gene B, and of course it's very simple. So the expected behavior, right, is an increasing response. So you're adding your inducer and the gene B is going up. So we did the experiment, right, very simple as part of a bigger project, and we got that, okay? That's definitely not increasing, so you can realize that pretty soon. It's very depressing because this is a very simple system, yet that's the first experiment. And actually, when we looked at this, we said, well, we can't even build a simple two-gene system, right? How can we build complex systems? And so we did a step back and looked at this in the context of the cell. If you now think that these genes are taking ribosomes and RNAP, and every time you are forcing a gene to express the protein, you are actually concentrating all these resources to that gene, less resources are left to the other gene. And so if this pulling force of these resources is larger than the regulatory link, you may very well end up in a situation like this, where the output ultimately decreases, okay? So bottom line, sharing limited resources can actually have pretty damaging results, okay, on your intended behavior of the circuit. And so in this talk, I will touch upon two main points. So the first point is really this notion of models and models, okay? So what are potential design-oriented models? So if you're looking for what people often call toy models, okay? But at least those are models that give us the ability to tune key coefficients that we can experimentally do in order to tune the strength, right, of these bad interactions. And the second part is really taking a control systems engineer approach, okay, and trying to defeat some of these perturbations. So here is the standard model of a gene regulatory network, like it's a textbook model. If you look at URL textbook, right, you have that the production rate of any protein, it's dependent upon field functions that have regulators, right? For example, UI are all the regulators of PI, some are activators, some are repressors, and alpha is a constant that tells you the maximal transcription rate or translation rate of the system, and it's dependent upon X and Y, which are the key resources for gene expression. RNA polymerase and ribosomes. So common models assume that X and Y are constant, but the reality, right, is that they are subject to a conservation law, right? So you have that the total amount of RNAP and ribosomes is equal to the free plus those used by each one of the genes, okay? So if you account for these and you do suitable quasi-steady state approximations, you can come up with a new model, okay, for the production rate of a protein. So now you have a new regulatory function here, which you can appreciate doesn't depend only on the intended regulators, UI, but also depends on other regulators that are not your own regulators, okay? And therefore, you have that through this coefficient JK, which we call resource demand coefficients, you have that your PI is going to depend also on UJ. And in particular, right, if this FJ is an activating function, it's going to actually appear as UJ being a repressor of your PI, okay? And the strength of these red interactions depend on this JK. It's a resource demand coefficient that depends on the DNA copy number D, on the amount of total RNA polymerase, and essentially on the ribosome binding site strength and the promoter strength, okay? So those are quantities, okay, that you can tune right in your system. So if you look at this now, your new regulatory function, you can look at what's the effective interaction graph of your network. And it turns out there are two components. So the first component is a rescaling of the existing regulatory interaction that you had before. So you still have that all these U affect your PI, but the strengths of this interaction become much weaker. And then you have a second part, which are hidden interactions that were not there. So these are not regulatory interactions, but they appear just because of this resource loading. Okay? So in summary, here are the effective interaction graphs, and these are rules that are independent of parameters. Okay? So anytime you have a regulator, which is a transcriptional activator, is going to act as an effective repressor for any other gene in the network, just because in the act of activating a gene is sequestering resources from any other protein. Similarly, if PJ is a repressor for any protein, it's going to act as an effective activator for any other protein, because in the act of repressing, it's freeing up resources, and so other genes can get activated. So then you have rules where, as I was saying before, the intended regulatory interactions just become weaker. And then there are some cases that are parameter dependent, and of course they depend case by case. So that's that. So this was an initial model that we created, and so we went ahead and did some experiments to validate it. So what we did the first simple experiment to verify that if we have an activation of one gene, in this case a red fluorescent protein, then it's actually becoming a repressor for any other protein. So, and as you can see here, as we are increasing the expression of the red, okay, actually the green is going down. And it's going down by about 70%, and this was in medium copy number plasmids, so that's pretty substantial. Something even more interesting is that if you're expressing this red gene with zero-strand ribosome binding site, so you have only mRNA, but not protein, the green is not affected. So that means that what's being competed for is mostly ribosomes or translational resources, okay? And this is going to be important for the fix to this problem. So that said, you can go back to the model and actually do a little bit of math to prove that any pair of genes in any network is always subject to this linear constraint, okay? Whenever you express one protein, the other one is going to decrease linearly. And if you do look at the data, that's what also the data confirms, okay? So anytime you express, in this case, a red protein, the green protein, which is unconnected, right, is just going down. You can do also something more sophisticated where you can demonstrate that you can tune the slope of this linear relationship by actually tuning the ribosome binding strand, right, of the protein you're looking at. So essentially you're tuning the price of the protein you're expressing. So we went back and looked then at what's the realizable region, and what you can prove is that in a simple case where you have two proteins and you have this ideal realizable region, the true realizable region is actually the intersection of simplexes that you can easily calculate from the model, but also to get from experiments. And of course, this is extensible to higher dimensions. But what I want to go back to is the cascade failure, okay? So it turns out that your activation cascade is not quite a cascade. It becomes an incoherent feed-forward loop because you have these hidden interactions, okay? And the strength of this interaction depends essentially on the DNA copy number, the ribosome binding site strength of the target, okay? So then you can create this parameter space, and you can move in it by tuning ribosome binding strength, DNA copy number. On the low end here, right, the hidden interactions are essentially really weak, while on the high end here, these interactions are really strong. So if you do an experiment and you start here, which is where we started at the very beginning, and you increase the DNA copy number, okay, then what you get that you're going essentially to destroy completely your cascade is monotonically almost decreasing. Then if you start to try to go back to the good region, which is the white region, then you can get back your desired almost cascade behavior. And if you move back in this regime, you get back your monotonically increasing cascade. Okay? So this is telling you that you can actually use in this model, simple, toy, design-oriented models, this resource demand coefficient to tune the strength of these interactions. So that said, so this is just to show you a tool, right, that we are using now with simple models to optimize the circuits. Okay? So, but the second part of the talk, which is the more engineering one, is really thinking differently. If I don't want to co-optimize my parameters, and I just want to make sure that the expression of a single module, right, is not changed by this resource depletion effect, how do I do that? Okay? So before I move to the second part, are there any questions on the first part? Yes?
I guess this assumes that the ribosomes are, there's no excess capacity there, for example, because the cell is growing. Otherwise, there shouldn't be competition.
Yes, so actually we did a lot of work. There are beautiful papers by Terence Hua and Klump, right? And so all our experiments and model are based on exponentially growing cells. And for exponentially growing cells, actually the number of RNP and ribosomes is quite well characterized, and they are limited. Yes?
I have the same question.
Okay, yeah.
So why the sum of, you say alpha p1 plus beta p2 is equal to yt? Like why is the
So yes, so it turns out that if you manipulate the steady state expression of the proteins, you can find that there is this manifold, this line where the protein concentration lie. And so the coefficients alpha and beta, they depend mostly on the ribosomal binding site strength. So they are somehow telling you the price that you have to pay to express that protein, okay? Stronger ribosomal binding site, lower price. Weaker ribosomal binding site, higher price.
but why yt the constant? Why the sum of these two proteins the constant?
Well, it comes out from the model, just solving the model and the data, right?
There's competition with other proteins. You don't. What's the effect of all the other proteins?
So actually, that's the effect, right? It's the fact that these two proteins become linearly related, right? If I didn't have competition, there would be any linear relationship, right, between these two proteins. They would just be constantly expressed.
I think he only had that result was for two proteins,
And
not for n proteins.
Yeah, it's only true for like
Yeah, that's
Any pair.
two constitutively expressed genes, or
Yes.
what's the condition to?
So the condition is that you have any two independently, so they are not connected, right? So any two independently expressed genes, right, produce proteins that they are linearly related that way. But if you have interactions, that's not true. Is that your question? So you have independent, right, expressed genes. Yes.
If you overexpress one protein and the overexpression of that protein decreases the expression of the target protein, it means that it must be decreasing the expression of all of the other proteins in the bacteria. And so the whole growth must be slowed down. I mean, isn't that a strong prediction of what you're saying? Because it's not just the target, but I mean, it must be everything.
Sure.
There's nothing special about the target.
So all my models assume that growth is not affected, and the data I've shown you has limited the induction level of each gene to a range where the growth is affected less than 10%. If you keep overexpressing the gene to the point that you are affecting growth rate, the models don't hold, right? Because this is assuming the growth rate is constant. Yeah. Any other questions? Okay, so that said, that brings me to the second part, okay, which is really this notion where, here is our system of intended regulatory interactions, and here is a system where we said there are these hidden interactions that occur because there is this resource sharing problem. So here is what I will do. I will view each one of these genes as my genetic module with regulatory inputs and regulatory outputs. And then I'll be viewing these interconnections through these hidden interactions as perturbations. And I will be looking to design a biomolecular controller that measures, the output of your system and regulates the expression of your module in order to compensate, for the disturbances WI. Okay? So that's the control problem I'm trying to solve. So that said, what's the problem here from a control theoretic perspective, right? We are trying to make sure that the input-output response of this feedback control system is insensitive to W, okay? So a traditional approach to that is to use integral control. So it's the notion where in your controller, right, you have a reaction or a dynamics that contains an integrator of the error between the outputs and the reference input, okay? under stability conditions, and I won't go into those details, y at steady state becomes independent of the disturbance, right, and essentially tracks only the e. Okay? So that's standard integral control, what works right in your automated cruise control and etc. Okay, so a challenge, right, if you want to design this in a molecular system, is that if we want to realize an integrator, we cannot, right? Because any protein is subject to leakage, right? So there is always dilution in the system, right, due to cell growth. This is especially true in bacterial cells that divide quite quickly, okay? And so the reality is that there is this leakage that you can't get rid of. So one approach is, if I can't remove this leakage, I can try to make all the other reactions in the controller faster, so that comparatively, right, the leakage becomes negligible. At least you hope so, right? So if you do that, we call this structure in which you have this fast controller action and this leakage quasi-integral control structure. So here is an example. So we have heard about this sequestration-based feedback mechanism that can implement an integral, right? So this has actually a leakage term here, and what I'm showing is that in the absence of leakage, right, and when you have disturbance, you have perfect adaptation. When you have leakage, then essentially you completely lose, okay, that adaptation property. But if you speed up the controller reactions, then you essentially rescue back that adaptation property. And you can actually prove this. It's a very simple, it's an application of the implicit function theorem, but essentially, if you can prove that the system without leakage, right, is globally asymptotically stable, then as epsilon becomes smaller, right, y of epsilon does not depend on your disturbance w, okay? So that said, this was an initial promising result that we felt very excited about, so we started thinking, okay, let's build the system and see if that works. Before going there, we actually started also asking the time-varying question, which turns out to be much more challenging. Okay? Here is what's the tracking performance of this quasi-integral control. So now let's assume that your input regulatory proteins, for example, is not constant as before, right? But it's time-varying. Okay? So in that case, standard approach could be to show, right, that this is a singularly perturbed system, so you set epsilon to 0 and see what happens, right? But you find out that this system actually belongs to a class of singular perturbation systems, where actually the boundary layer dynamics is not asymptotically stable, okay? So there's a 0 eigenvalue, okay? And so essentially we don't have an equilibrium point unless u is equal to y, which is actually what you would like to have, okay? But you can't prove this using Tikhonov theorem, okay? So then what we did, we stepped back and we said, let's look at the linearization, okay? So what you find out from the linearization is that actually, even though this seems to have two fast variables, there's actually just one fast variable. And as you decrease epsilon, the other mode becomes less and less damped, okay? So you have these decreasing damping ratio of these poles that get close to the origin, okay? So what we had to do is to prove a Tikhonov-like theorem for general linear SSP systems. So if you can prove that there is a coordinate transformation that takes the system to the true fast-slow variable partition, and the reduced system is a high feedback through 1/epsilon connection of strictly positive real systems, then you can prove that actually this result is almost true up to order square root of epsilon. Okay? So this is different from what you get in singular perturbation, where you would get here an O of epsilon. Okay?
So what's the rate of change of u in that equation?
So here u of t we are assuming is much slower. Okay? Than
So it's implicit in your formula.
Yes.
I didn't say. I
Yeah.
see. So it scales with epsilon in some way.
Yeah.
Okay.
So that said, right? Are there any questions on this? So that said, okay, we thought, okay, let's build a system, okay? And we did it. So we searched for a pair of molecules, M and S, that could be part of our controller. So we picked essentially a system where our mRNA of our protein is targeted by an sRNA, which is expressed by this feedback loop here. So the sequestration reaction is actually here. M and S come together and go to nothing. Okay? These mRNA-sRNA interactions have been modeled really well before by others. And it turns out that you can demonstrate that there is a hidden variable in the system that is an integrator. And the conditions required, right, for tracking, right, are satisfied. The key thing is that all the controller reactions of mRNA and sRNA must be much faster, okay, than dilution. Okay? So here is the system implementation. So we have two systems here. One is a system which is expressing this GFP gene, and which in here should be constitutively expressed. And here it's our resource competitor. So we are expressing RFP, which is sequestering ribosomes. Okay? And here what we are doing, we are having this GFP expressed in a pieces running operon with the sigma factor, which is activating the sRNA, and then you have this feedback. So that's that. Here is the temporal response after you are inducing the resource competitor. So at this time, you use the resource competitor in a system without the feedback, so you don't have any sRNA here. And you can see that, as seen before, the GFP level goes down. But when you close the loop, so you have your sRNA, you can see that upon application of this perturbation, your GFP gene expression goes down, but then it recovers. Okay? You can also see what happens on the distribution. So essentially, the distributions go back together, very different with respect to the open loop system, where the distributions are also very different. And here is showing what happens if you keep increasing the expression level of this protein. Right here, you're really overexpressing this protein. Yet your controller is able to maintain almost, okay, the same steady state level of your protein. So anyways, so this is essentially reaching the end of my talk. So here is a summary, right? So I have touched upon a few sources of context dependence, and I focus on this notion of loading cellular resources as a major problem coupling systems among each other. I've shown you a design-oriented model to actually be able to tune the strength of these hidden interactions for design. And then I've shown you our current approach, okay, to design the systems in such a way that they can be modularly composed because they are not affecting each other. So that said, I would like just to thank the people that contributed to this work. So Ili and Sinho are the key players in this. Actually, Ili is here in the back of the room. So if you have more questions about either the theory and the experiments, just go and ask him. And that's about that. Thank you.
Okay, we have a few minutes for other questions.
Yes.
So you have an interaction graph in which the y-axis is the RBS strength and the x-axis is the DNA copy number. How do you incorporate these two into the model? Like, how do you model DNA copy number in your model?
So the expression level in the model of every gene, so the transcription rate, is always proportional to the DNA copy number. So that's where it appears.
What's the effects of the RNA polymerase and ribosome?
Yes, so I didn't show you a lot of data, but essentially what happens is the RNA-P is not limiting in this case. So we did experiments where we only express the mRNA, but not the protein. And essentially, that means that you're only sequestering RNA-P, and that has no effect on the level of the constitutive protein. So that's telling you that, at least in the growth conditions that we are considering, RNA-P is not limiting.
For bacteria?
Yes, this is all bacteria, exponentially growing E. coli.
That experiment on body is showing that if you express like
Sure. We have experiments in mammalian cells, and the story is very different. That would be a completely other talk. So in mammalian cells, actually transcription is the bottom.
Is the result on bacteria depends on the condition, the nutrient, or the growth rate?
Of course. So this is all in exponentially growing bacteria at 30 degrees, right? Very controlled.
But what that depends on if it's slow growth or fast growth.
So fast growth or slow growth tells you the number of total RNA-P and ribosomes in the cell. right? So there is a beautiful paper by Karen Swa, right, that demonstrate that the number of ribosomes is proportional, right, to growth rate.
Okay, any other?
Could an alternative solution be to just harm the growth rate so that there will be excess capacity, so that this doesn't... Could you just dampen the growth rate by some method so there will be remaining excess capacity that you could use?
Yeah, so absolutely. That's a great question, actually, right? So here I'm just looking at this one genetic modules and trying to make it isolated from the rest. But another approach, right, would be, can you regulate growth rate, or can you even regulate free ribosome level, right? And there are other people, there's beautiful work, right, from the UK, from Deepak Stan, right, and Tom Ellis that are actually looking at that question. Yes, absolutely.
Okay, let's thank the speaker again.